Good morning. Welcome to yet another episode on this channel. Today we are going to be looking at the Chinese remainder theorem. But before we do that, let's look at the exercise that I gave the last time. So this is the solution to that exercise. And if you go through, I have solved this. Looking at the question 2 over here, because the GCD of 7 and 42 was not equal to 1, I used the fast exponentation procedure to solve this problem. So 3,444 was divided into 2. So over here I used modulo 2. So looking at this, if you find the modulo 2, the 0, 0, 1, the one that you see over here are all the remainders, and the ones in black was the exponents. So if you divide 3,444 by 2, you are going to get a remainder of 0. If then over here you divide 344 by 2, then you have 1722. 1722 in mod 2 is also 0. Then you divide it by 2 again. So you do that till you get to the last number, which is 1. And this is the question 3 as well. So the question 3, I solved s raised to power 20 equal to 1. So we use the same procedure. I use the same procedure that we used the last time. Now let's look at the Chinese remainder theorem. Okay, so when it comes to the Chinese remainder theorem, let's consider this. That's the theorem. Let M1, M2 to Mk be integers greater than 1. If M1, M2 up to Mk are pairwise co-prime, for any integers a1, a2 up to ak, then there exists an x such that s is congruent to a1 mod m1, s is congruent to a2 mod m2, then s is congruent to ak mod mk. And also, moreover, there is exactly 1x in the set Zm where m, so over here the m over here is the capital, so Zm where m is equal to small m1 times small m2 all up to mk. So all solutions of the congruence of, so this is the, over here when you say the congruence, this is the congruence. Okay, so all solutions of the congruence have the form x is equal to a1 m1 n1 plus a2 n2 m2 plus ak mk and nk plus your big M t, where t belongs to z. Okay, so now this is the theorem. First of all, you'll be given congruences. So now after having the congruences, then you solve this. So first of all, you have to find your m1, then you find m1, m2, m3, then afterwards you find your n1 up to your nk, then you find your big M. So let's solve an example to see how this one works. So our first example is, so solve the system of congruences. If you have x is congruent to 5 mod 7, x is congruent to 7 mod 13, and s is congruent to 12 mod 17. So now having this, the first thing that you have to do is, first of all, you have to find your big M. So your big M is equal to, over here, your M1, M2, M3. So M1 is 7. So M1 times your M2 times your M3. So that is 7 times 13 times 17. And that is equal to 1547. Now, before you can go ahead and solve this, remember that in the theorem, it said that if m1, m2 up to mk is pairwise co-prime, so we have to check if m1, m2, and m3 are pairwise co-primes. So like if it is, then the GCD of 7 and 13 should be equal to the GCD of 7 and 17. It should also be equal to the GCD of 13 and 7, and this, sorry, 13 and 17, this should be equal to 1. Okay, now after doing this, we now find our big M1, M2, and M3. So M1 is always equal to your big M over your small m1. So big M was 1547, and our small m1 in this case is 7. We are going to get 2 to 1. Now m2 is also going to be your big M over small m2. So big M is 1547 over small m2, which is 13. We are going to get 119. Then m3 is equal to big M over small m3, which is equal to 1547 over small m3, which is 17. And this will give you 91. So after doing that, after getting our big M1, M2, and M3, now we have to look for our N1, N2, and N3. So we determine N1, N2, N3 using the Euclidean algorithm. So in finding our n's, we are going to do this. So first of all, let's find n1. n1 times m1 is always congruent to 1 modulo small m1. Now our big m1, we saw that our m1 is 2 to 1. Multiplying n1 should be congruent to 1 should be congruent to 1 modulo, and our small m1 was 7. Now after getting this, we have to then write 221 in terms of modulo 7. So 221 will always be congruent to, in mode 7, I'm going to get 4. So 4 mode 7. And after doing this is the same as writing 221 n1 is always congruent to 4 n1, which is congruent to 1 mode 7. So in practice, what we are trying to find is we want a certain value that if we multiply by 3, we should get a remainder of 1 in modulo 7. So we can use the Euclidean algorithm to do that. So you can find 4 inverse in mode 7, or you can also check if because the numbers are too small, we can check, okay, 4 times what will give us 1 in modulo 7. So 4 times 2 is 8, and 8 in 8 mode 7 is 1. So we can see that n1 in this case is 2. If we use the Euclidean algorithm, we're going to get the same thing. Now let's find our n2. So n2 times big M2 will also be congruent to 1 mode small m2. And we got to see that m2 is 119. So 119 n2 is congruent to 1 mode small m2, which is 13. So we have to write 119 in terms of mode 13, and that is 2 mode 13. So the same thing, 119 and 2 is congruent to 2 and 2 1 mode 13. And now we want a number that if we multiply by 2, we are going to get a remainder of 1 in mode 13. And if we go to the Euclidean algorithm, you are going to see that n2 is equal to 7. 2 times 7 is 14, and 14 mode 13 is 1. And now let's find n3. So m3 is congruent to 1 mode m3. Now m3 is 91. So 91 m3 is congruent to 1 mode small m3 is 17. So we have to write 91 in terms of mode 17, and that is 6 mode 17. So 91 n3 is congruent to 6 n3, which is also congruent to 1 mode 17. Now doing the same thing, we are going to get n3 to be equal to 3. Now after getting this, remember our congruences will always be of the form S is equal to A1 M1 N1 plus A2 M2 N2 plus A3 M3 N3 plus our big M times T. So now A1 is equal to the value over here. So the coefficient of mode 7, which is 5, is your A1. The number in front of mode 13 is your A2, and the number in front of mode 17 is A3. So A1 in this case is 5. So you're going to get 5 times your big M1, and big M1 was 221 times N1. N1 is 2 plus A2. So A2 is 7. Big M2 is 119, and your N2 is 7. A3 in this case is 12, and your M3 is 91, and N3 is also 3. But note that your big M, which is 1547, is also multiplying T. And after doing this, you get to see that S is equal to 11317 plus 1547T. So now to find your x, s is the same as doing this 11317 mode 1547, and this is going to give you 488. So now the answer of this is 488. So the congruence over here, 5 mod 7, 7 mod 13, and 12 mod 17. So when we say that S is congruent to 5 mod 17, then in this case it means that if we have this, S is congruent to 5 mod 17 and X is 488, meaning that 5 mod 17. So if we want to see that indeed this is right, we can interchange the 488 and the 5. So we can say that 5 is congruent to 488 mod 17. Now what is 488 mod 17? Sorry, okay. So sorry, the first one was S is congruent to 5 mod 7. And now our X is 488. So 5 mod 7. Now if we interchange 488 and 5, you're going to get 5 is congruent to 488 mod 7. So what is 488 mod 7? It's indeed 5. Then it works. You have to do the same thing for the second congruence. So the second one is 7 mod 13. So 488 is congruent to 7 mod 13. So if you interchange it, you're going to see that 488 mod 13 is indeed 7. So 488 mod 13 is indeed 7. Then you do the same thing for the last one, which is 12 mod 17. So 12 mod 17. So 488 is congruent to 12 mod 17. So meaning that 12 is congruent to 488 mod 17. So it works for all three congruences. Now, if you get a value of x and it doesn't satisfy even one of the congruences, then it means that there is a problem with your solution. So this is how to solve any Chinese remainder problem. I will see you in the next video. Thank you.